Okay, let's find the Maclaurin series for f of x using the definition of the Maclaurin series, meaning we have to go through the process and find all derivatives. So we know the Maclaurin series is just a Taylor series centered at 0. So we put in 0 for our a here and 0 for our a here. And basically we got to go through the process to find a pattern to plug in there. So we're going to go take a bunch of derivatives. So we got ln of 1 plus 2x, taking the derivative will be 1 over 1 plus 2x, times the derivative of the inside, which is 2. I can rewrite that maybe like this, with a negative 1 exponent, so that the next derivative will be easier to analyze. So I'm going to go take the second derivative now. So let's bring down the negative 1 plus 2x to the negative 2, times the derivative of the inside, which pops out at 2, and I still have this other 2 waiting outside. I'm not multiplying anything out because I want to see a pattern. Third derivative, the negative 1 was there. I'm going to bring down the negative 2, 1 plus 2x to the negative 3. Chain rule derivative of the inside, pop out at 2, and these two 2's were still waiting there. Let's go one more time to the fourth derivative. So I have the negative 1, the negative 2, and I'm bringing down the negative 3, 1 plus 2x to the negative 4. Chain rule, pop out derivative of the inside, and then these 3 2's were still waiting around for me. So basically what I have is I have a 2, I guess, over 1 plus 2x to the 1. And then I have 2 2's there. So a 2 squared over 1 plus 2x to the 2 with a negative 1 waiting outside. And then in the next one it looks like I have a 2 to the cubed upstairs, and I have a 1 plus 2x to the third downstairs. And I also have this negative 1 and this negative 2, which end up being a positive. And since I see a 1, 2, 3, and I know I'm going to see a 1, 2, 3, 4 if I do it one more time, so if you need more derivatives, just do that for yourself. I'm thinking that's just going to be a 2 factorial. 2 negatives will make a positive, and that'll just give me a 2 factorial there. And for the next guy, I have 4 2's. So 2 to the 4th in the numerator. And then I have 1 plus 2x to the 4th in the denominator. Then notice I have the 1, 2, 3, which is just 3 factorial. And then I have a negative out in the front. So let me clean that up a little bit. Okay, let's go kind of try to see the pattern. This guy looks different from the rest of them. So I'm not going to worry about that for right now. The first derivative, when n was equal to 1, it looks like I have 2 to the 1 upstairs, and then I have 1 plus 2x to the 1 downstairs. So first derivative, n equals 1, I see 1's there. Second derivative, n equals 2, I see a 2 to the 2 upstairs and a 1 plus 2x quantity squared downstairs, and I also see a negative sign, whereas at the beginning this guy was positive. Then when n is 3, so third derivative, I see a 2 cubed upstairs and that other quantity cubed downstairs. Now I see a 2 factorial. And 2 is 1 less than 3. So I'm guessing, would that work for this one also? And it looks like it does. When n is equal to 4, so when I'm looking at the fourth derivative, I have a 2 to the 4th, that quantity to the 4th, a 3 factorial outside, and I have a negative. So I'm having positive, negative for the pattern of the signs. I have a 3 factorial, a 2 factorial. I could think of this guy as a 1 factorial if I wanted to, and I could think of having a 0 factorial in front of this guy, because 0 factorial is just 1 anyway. So if I'm to follow the pattern, I think we can figure out what the nth derivative should look like. The nth derivative at x, for any general x, I'm trying to figure out the pattern because I'm going to eventually go put 0 for the Maclaurin, but if it was any other number, I would put the other number there. So I definitely have a 2 to the n in the numerator, because fourth derivative 4, third derivative 3, second derivative 2, first derivative 1, and so on. Then I also know for sure I have 1 plus 2x to the n in the denominator because the n's and the derivatives match up. The thing that's different is the factorials in the front. They're always 1 less than the derivative I'm at. So if I'm at the fourth derivative, I have 3 factorial, third derivative second factorial, second derivative first factorial that I made up over there myself. So I'm going to have in the front an n minus 1 factorial because I'm 1 short of the n location that I'm at. Also, I have to adjust my signs so they can alternate. So I'm just going to put a -1 to the, let's see what I should put there. When n is 1 and positive, or when n is 1, we have a positive term. So I can't have it to the n. I should adjust it and make it an even power. So when n is 1, 1 plus 1, 2 will give me a positive. When n is 2, 2 plus 1 will give me 3, which is a negative, and then a positive and a negative, and so forth. Now I'm going to analyze this guy at 0. So when x is 0, the nth derivative at 0 will just still be the -1 to the n plus 1. It will still have the n minus 1 factorial. I will still have the 2 to the n. All I'm doing really is going in the denominator and inputting a 0 for the x. So it looks like I end up with 2 times 0. That makes that go away, just I guess a 1 to the n in the denominator. So who cares about the 1 to the n? That means I pretty much have my nth derivative at 0 as this guy. That now matches up exactly with what I was looking for to put in here. So now I pretty much have the Maclaurin series. I just need to go plug things in and simplify. So f of x, which was ln of 1 plus 2x, can be written in this form with the Maclaurin series. We did go ahead and find this guy to plug in. However, I should be careful because remember what we had done. The first guy looked completely different. It didn't follow the pattern. This is when n was equal to 0. So when n was equal to 0, it looked different than the rest of them. So I shouldn't put n equals 0 inside the sum because it doesn't follow the pattern. So I'm going to take n equals 0 outside and then start my sum at 1, so it'll pick up all of these guys that have that pattern going along with them. So let's go over here and plug that in. So when n is equal to 0, I basically have this to evaluate at 0. So when n is equal to 0, I'm simply looking at f of 0. I'm not taking any derivatives, and f of 0 is just ln of 1 in this case, and that's just 0 anyway. So the very first term when I let n be 0, which is, remember if I open this up, it's going to be f of 0 over 0 factorial plus f prime of 0 over 1 factorial x to the 1, that was x to the 0, and dot dot dot. So we are able to pick things up from here on. We can get these coefficients with this nice pattern, but the very first guy looked different. So just f of 0 is ln of 1, which is still 0, 0 over 0 factorial is just going to be 0. So it doesn't really contribute anything, but I'll go and put it there. So when n is equal to 0, it spits out a 0, the first term that was looking different. Everybody else from 1 on follows this pattern, so I'm going to put it inside the cloud, -1 to the n plus 1, n minus 1 factorial, 2 to the n, everybody over n factorial, x to the n is what ln of 1 plus 2x should look like. But we could do a little simplification here. This is just n times n minus 1 factorial, so all of this guy and all of this guy go away. and we end up with n starting at 1 to infinity of -1 to the n plus 1, 2 to the n over n are the coefficients, x to the n as our power series. So that's the Maclaurin series for ln of 1 plus 2x. We also have to find the radius of convergence, so let's go figure that out. So I'll just use the ratio test to figure out the radius of convergence. You can use the root test or ratio test, your choice. Root test might have been quicker because it's raised to the nth, but I already wrote it down, so let's continue with this. I ate the negative because it's just taking absolute values. So it looks like 2 to the n times 2, x to the n times x. This and this go away, this and this go away. And it looks like I end up with a 2 and an x in the numerator, which I'll take outside since they are independent of n. And inside I also have n over n plus 1. We know this guy just goes to 1, so the limit is just 2x in absolute value. We need that to be less than 1 for convergence. So 2 absolute value of x is less than 1. Dividing both sides by 2, it looks like x has to be less than a half in absolute value. So the radius of convergence for this power series is a half. I also want to point out that we did this using the definition of the Maclaurin series. So we went through all the derivatives and tried to find a pattern for the nth derivative at 0. We could have also done this by using integration and differentiation ideas and tracing it back to the geometric series we worked with, which was 1 over 1 minus x. So just a quick note, we won't do it in its entirety. If I have ln of 1 plus 2x, I could think, alright, what should I start with? And I could start with differentiating that will give me 1 over 1 plus 2x, derivative of the inside is 2, so I have 2 over 1 plus 2x, as maybe we'll call it g of x to start with. So if I start with this guy, I can write that as 1 over 1 minus box, and then this will help me rewrite that as negative 2x to the n. And then we can quickly clean that up a little bit. So that's negative 1 to the n inside. And then I also have a 2 to the n. I'm also going to move this guy in. That's going to be 2 to the n plus 1, x to the n. So that'll be my g of x. And we do know that if we integrate g of x, we're going to go back to this guy f of x. So your next step would be to integrate basically both sides, and once you integrate both sides you will get your f of x, which is ln of 1 plus 2x, and integrating this side will give you the power series or the Maclaurin series representation for this guy. So you have options. You can either apply the Maclaurin series definition or do it the way we did in section 11.9, where you compare it to 1 over 1 minus box business.